Alright, so in this video we're going to be talking about heating and cooling curves and also what happens when you heat a substance up and it actually goes through a phase change. So when you have a phase change happen, so whether it boils, melts, evaporates, condenses, whatever, when that happens, the energy, if you put energy into a substance and you're melting it, boiling it, the energy goes into breaking up those intermolecular forces between the molecules so that they can go to the next phase. Now, if you were to do the opposite and take energy out, that energy is being taken out of the molecules, so they're actually moving closer and closer together to change phases. Now, when this happens, none of the energy actually goes into changing the temperature. It all goes into breaking those intermolecular forces or recreating them. So if you freeze or melt a substance and you want to know the energy that goes into it, you could take the number of moles, which is N, and multiply it by something called delta H of fusion. So this is the molar heat of fusion. It's a constant value. It'll be different for every substance, and this is the same number is going to be used whether you freeze or melt something, and it will be positive or negative based on what you're doing. So if you're melting a substance, you're putting energy into the system, which means that delta H would be positive. If you are freezing something, then you're actually removing energy from those molecules as they come closer and closer together, so the delta H of fusion would be negative. Now, this is something that a value that they would have to give you. So if you freeze or melt something, you would use this equation to find the heat energy that's involved in that process. Now, if you boil or condense, it's the same formula. You're going to use the number of moles and multiply it by something called delta H of vaporization. So this is the molar heat of vaporization. Again, it's a constant, and it will be positive or negative depending on what you're doing. So if you're boiling it, you're putting energy into it, which means that the value will be positive. If you're condensing it, you're removing the energy and they will be negative. Alright, so this is what it actually looks like if you heat up a substance. So the temperature does not just go straight up. It actually stops at certain points and just remains constant. Anytime that you see a flat line on a heating curve, it indicates a phase change. So the flat lines will be a phase change. So when you're heating up a substance, and you can tell because the temperature is going up, you're going to start at a solid. Well, normally you will, especially if you see two flat lines, that indicates that you have two phase changes. So right here, from this point to this point, I actually have a solid. And I can see the temperature is increasing. So basically at this point I am increasing the temperature of that solid. Well, from point B to C I have a phase change. So what I can assume at this point, since I'm starting at a low temperature, I am at a solid state. So at this point I'm going to be going to the next state of matter, which would be a liquid. So I am melting that substance. So there is no temperature change while I am melting the substance. So this would also be the melting and the freezing point of that substance. So right here, once I finish melting, I should be in the liquid state. And again, the temperature is going from here to here, so it's increasing again. I have another flat line right here, so that indicates a phase change. Well, if I'm in a liquid and my temperature is going up, I should be boiling the substance here. So this would be the boiling point of that substance and also the condensing point. It's the same temperature, it just depends on what you're doing with the energy as to where it's going to go. And then right here from E to F, that should be when I am at a gas, and the temperature will be increasing here as well. Alright, let's look at a cooling curve. Cooling should be the opposite. I should start at a high temperature and then go to a low temperature. Since I'm starting at a high temperature, I can assume right here I'm at a gaseous state. And my temperature is decreasing. Well, I'm at a flat line, so I have a phase change. So since I am going from the gas state and I'm cooling it down, I should be condensing at this point. And then right here, I can actually read the temperature and say, okay, it's 150 degrees Celsius, so that's actually my boiling point, and it's the same temperature that the gas would start to condense. So once we get to this point when the temperature starts to change again, I should be in the next state of matter, which would be the liquid. And my temperature is decreasing here again until I get to about 90 degrees Celsius. So since I'm going to a liquid to the next state down, that would be a solid, I should be freezing at this point. So the freezing point should be 90 degrees Celsius, and it's also going to be the melting point. It just depends on what I'm doing with energy as to what it's going to do. And then at this point, I should have my solid state, and my temperature will be decreasing here. All right, so just to kind of recap, if we are going through a temperature change with a substance, we're changing the kinetic energy. So how the molecules are moving. That's going to depend on the heat capacity of a substance. If it's going through a phase change, I'm not changing the temperature, it remains constant. And what I'm actually doing is I'm changing the potential energy or the molecular arrangement of molecules. All right, so consider the following data. You have all of this. How much energy is released when 1 mole or 18 grams of water is at 20 degrees Celsius is frozen and then cooled to a temperature of -2. Okay, so let's go through this and see what information we have. Okay, so you have the problem in front of you. You should be reading it as I go through it. So it says we have water. So first of all, I know the substance is water. We have 1 mole of that water. And then it tells us that the mass is 18 grams. So N would be the number of moles, M would be the number of grams here. It says that the initial temperature of the water is going to be 20 degrees Celsius. And then it says the final temperature that we get to is -2 degrees Celsius. All right. Now, we do know that if we're looking for heat energy in a system, we can use this equation. However, if you notice, you go from 20 degrees Celsius to -2 degrees Celsius. So anytime you have one of these types of problems, you need to figure out, did I go through a phase change? And it does tell you that you go through a phase change here, but you also know that the freezing point of water is 0 degrees Celsius. And I know that the boiling point is 100 degrees Celsius, but we're not even in that temperature range, so I don't need to worry about that. So I know the freezing point of water is 0 degrees Celsius. So once I'm cooling down this substance, it goes from 0 to 20 to 0. And at 0 degrees Celsius, something happens. It freezes. So in order to find out the energy change at that point, I have to use this. So anytime that we go through a phase change, you cannot use this because the temperature is not changing. You have to use this equation instead. Okay, so let's pull out the rest of the information that I need. Or actually, before we even do that, let's go and divide everything out into steps. So basically, whenever your temperature is changing, you can use this equation to find the heat. We cannot just simply plug this information into this equation right now because we go through a phase change. So if we didn't go through a phase change, yes, absolutely do this. But since we're going through a phase change, we have to divide everything out into steps according to when the substance changes phases. So the first thing, I know it goes from 20 to -2, but at 0, something happens. So that's my first step. So step 1, the temperature changes from 20 degrees Celsius to 0 degrees Celsius. Now, once we get to 0 degrees Celsius, we are freezing. Now, once I actually have a solid, then I can bring the temperature down even further to the -2. So basically, you divide everything out into steps according to when your phase change happens. So if we were going from a solid to a gas, we would have to include 2 phase changes, and then that's how you divide out your steps. So from step 3, we're going to go from 0 degrees Celsius to -2 degrees Celsius. All right, so when I do this, let's look at the rest of the data really quick. It gives us specific heat capacities of ice, water, and steam. This is something important here. You will use the specific heat capacity according to what state of matter you have. It changes. So you have to be really careful about which C you are using. All right, and then also you have to be very careful about your units. So if I look at this, all of my C's are in joules per gram degree Kelvin. So I'm going to change my temperatures to kelvins. So 20 degrees Celsius should be 20 plus 273 should be 293 Kelvin. 0 plus 273 would just be 273 Kelvin. It should be 273 too, although that does not matter at this point. All right, so this 0 would be 273 Kelvin, and -2 would be 271 Kelvin. All right, so in step 1, we have a temperature change, so we're going to use this formula right here. So what we're going to do, we need to find the heat in each step. To find the total heat energy that goes into this process, we need to get the heat at each step, and then at the end, we're going to add them together. So we're going to use Q is equal to MCAT. I have the mass, and for C, since we are at 20 degrees Celsius here, we should have a liquid. So we are going to use the specific heat capacity of the liquid, which should be 4.18 joules per gram Kelvin. So I'm going to plug everything into Q equals MCAT. 18 grams, so that's my mass. C for the liquid will be this. And then my change in temperature, final minus initial, should be 273 minus 293, -20. So you should get a negative delta T here because you're going from 20, or you're going from 20 to 0, so it's final minus initial. Okay, so when I solve to get the heat energy here, I'm going to get -1512 joules. All right, so now let's go to the next step. Well, we're freezing. There's no temperature change when you have a state of matter change, so we're going to use this equation right here. So delta H, same thing as Q pretty much. That's equal to N, which is the number of moles, times delta H of fusion. So if I go back, it tells me this right here, it's 6.02 kilojoules per mole. We use fusion when we are freezing or melting. We use vaporization when we are boiling or condensing. It's kilojoules per mole. All right, so when we freeze a substance, we are removing the energy, so this is going to have a negative value because we are freezing. So it's going to be negative 6.02 kilojoules per mole. So when I solve for this, delta H is equal to negative 6.02 kilojoules. Notice our first step is in joules. Okay, so let's go to the next step. We're going from 0, so once I freeze, I'm still at 0, and then I'm going to go cool it down to a negative 2 degrees Celsius. So there's a temperature change. I'm going to use MCAT. So Q is equal to mass, which is 18, times the specific heat, but we have to be very careful about which one we're using. After we have frozen the ice, we have a solid state of matter. So my heat capacity of ice is 2.05. So I'm going to use 2.05 here, not 4.18, because I have to consider the state of matter. It changes. All right, so final minus initials, 271 minus 273. So when I solve for Q here, I'm going to get negative 73.8 joules. So now if I want to get the total energy involved in this process, I'm going to add everything together, but I have to be very careful about my units. I have kilojoules here, joules and joules here. So I'm going to convert this to joules. It should be negative 6,020 joules. So this plus this plus this. So the heat total will be this plus this plus this. So I should get negative 7,605.8 joules. So in order to freeze the ice from 20 to negative 2 degrees Celsius, I release 7,605.8 joules. All right, so let's look at the rest of the problem. Considering only the energy released in the phase change above, what would the temperature rise observed in the heat bath made of gold that has a specific heat capacity of 0.129 joules per gram per Kelvin with a mass of 0.52 kilograms? All right, so let's go ahead and sort out the information. So basically it's saying if you take this energy and then put it into heating up gold, what is your change in temperature of the gold going to be? Okay, so where is this? So my heat that's released from the bath is negative. Yes, okay, so if I take this energy and I use it to heat up gold, well, it's no longer going to be negative because I'm going to absorb it into the gold. Okay, so this is for the gold. So let's sort out the information we're given. This is the water freezing, and then this is going to be the gold. All right, well, it tells us a few things. It tells us that the specific heat capacity is 0.129 and the mass is 0.502 kilograms. So the mass of the gold is 0.502 kilograms. Specific heat of the gold is 0.129 joules per gram Kelvin. And it's asking what is the temperature change going to be if I use this energy to heat up the gold. All right, so first thing, let's check our units. We have kilojoules and joules. We can't have that. So that's going to be 502 joules. And grams. Oh, this is not kilojoules. This is kilograms. And then this will be grams. Joules and joules, that matches. Grams and grams, that will match now. So now we can just simply plug it into Q equals MCAT. All right, so Q is this, 7,605.8. Mass is 502 grams. Specific heat is 0.129. And delta T is unknown. Well, my grams will cancel, my joules will end up canceling, and I'll be left with Kelvin. So once I solve for this, for delta T, I should get 117, and I will be left with Kelvin. So the temperature will go up by 117 kelvins here. Okay, so just a quick recap. When you do this, when you go through a phase change, divide everything into steps. Okay, divide into steps. So every time you have a phase change, it's a new step. So if you pass the boiling point, if you pass the freezing point, BP or the freezing point. Okay, so if your temperature is going up, you need to divide it up into points of boiling point and the melting point. Remember, when temperature changes, you can use MCAT. When you go through a phase change, you use the number of moles times the heat of fusion and the heat of vaporization. So you're going to use delta H of fusion when you either freeze or you melt. And then if you freeze, it's negative. If you melt, it's going to be positive. You use delta H of vaporization when you boil or when you condense. So if you boil, it will be positive. If you condense, it will be negative. And then also make sure you use the correct C. So if you are in a liquid, make sure you use a specific heat for liquid, solid, solid, and so on. And then also units. Check your units every single time you do a calculation.